In this video, we shall explore a less trivial situation where we shall make a linear model using the black box approach. We shall again work with that spring example, but this time we shall use two different types of spring. Now both the springs are effectively very similar, made out of same kind of material, same material, but they have some difference which we cannot ignore. That is something that we cannot just sweep under the rug of random error. Now this scenario is a very common one that we experience in practice, where you have to work with certain units or systems like plots or patients, but you do not have enough of those systems in one place. For example, you need to work with lots of patients, and one single hospital will not be able to provide that many patients, so you spread out your research over multiple hospitals. Then each hospital will bring its own unique factors. They may not be the most important factor, they might become important, so only the study can tell that, but at least your primary goal is not to study the difference of the different hospitals. But still, those differences may not be ignored. Similarly here, I will pretend that this thing, say, comes from one lab and this thing comes from another lab. They have same types of spring. However, you can see that here the length is less than the length here. So there is some difference. It's not random difference. Our aim is not to investigate the difference of length. Our aim is to investigate the behavior, elastic behavior of the spring. With respect to that, they are both same material, same geometry, same radius, etc., etc. Now, how do you deal with this thing using a black box? The solution may not be that obvious. In this case, the particular thing that we use will be this black box. Now, this black box has, again, that spring, one input, that is the weight, and the usual output, that is this length. However, it has got another input, that is the lab. Now, observe this carefully. The lab is not what you'd naturally think of as input. It is not that there is something called a spring to which you applied an effect of lab. Lab is already there. So this spring comes from, say, lab 2, and that spring comes from lab 1. But when we want to make the black box, we consider this spring, what we have written inside that green box, that is the abstract notion of spring, what we want to study. Now we have different types of springs, so that also is actually an input. So in this case, we have got two inputs, weight, that's a covariate, a continuous one, and lab, that is a categorical input, a factor. And the output is, as before, just our length. So you hang different weights in lab 2, you hang different weights in lab 1, you make the measurements, and as a result, from the two labs, you will get two sets of data. Say you get this from lab 1, and this you get this from lab 2. So you have different weights, and you have got different weights, and you have got different lengths. All these things come from lab 1. Similarly, all these things come from lab 2. Observe that the two labs may or may not use the same set of weights. For example, here I can see 1.5 has been used in both the cases. Of course, the elongations are different, the lengths are different because they are working with springs that started with different initial lengths. Some of the weights, in fact, most of the weights are different from this lab to that lab. In this case, one particular weight has been repeated. So it is a repeated measure experiment, which is the most common thing in practical scenarios, where you hang the same weight a multiple number of times and take different measurements just to get an idea about the effect of the random error. So you get one Excel file like this from one lab and another Excel file like this from this lab. Now the question is, how do we combine them? Because remember, R or any other software needs one single data set to do the analysis, not two different data sets. So how do I merge them? The technique to merge them is to put one under the other. So you take lab 2 and put it under lab 1. That's like a longer table. But somehow we have to tell R that these things come from lab 1 and these things come from lab 2. We achieve that by adding one additional column called lab. So I have got one additional column called lab, which says that in this case, all these things come from lab 1 and all these things come from lab 2. So now I have got a table with 3 columns, WL lab. Observe that in our black box we have exactly 3 arrows other than this unobservable random error. I have got W, and you see I indeed have one column for that. I have lab, I have another column for that, and I have the output L, I have one column for that. This is always going to be the case. You will always have exactly one column per arrow in the black box diagram, irrespective of what model you are going to fit. So this data layout will always depend on only the black box diagram. Okay, so now that we have this, it will help if we just express symbolically all these quantities in a slightly different way. So earlier we had called these things WIs and LIs. Now, once we have this factor input, a more useful way of denoting this thing is by using two subscripts. Now, understand this carefully. Whenever there is some factor input, you must dedicate one subscript for that factor. And one subscript, we might say, is dedicated to the random error thing. So earlier we had only weight and length. We did not have any factor input. So we had only the random error. So we used only one subscript. In this case, I have got lab, that is the factor input, and I have dedicated the first index, I, to that lab. So here, for example, Wij means the weight that you hung in the jth trial in the ith lab. For example, what is W11? W11 is this 1.0. Lab 1, trial 1. W12 will be this 1.5. Lab 1, trial 2. Similarly, W21 will be lab 2, trial 1, that is this 1.2. And this is W22, W23, W24, W25. So J basically indicate that when your factors are all at a particular value, fixed at a particular value, you are just carrying out the experiment again and again. That's why I just say, just remember that it is dedicated to this random error. So that is the idea. You are doing it again and again with the same setup in terms of the factor. The covariate may or may not change. In this case, the covariate has not changed. Also notice that the J index, the range of the J index may depend on I. When I equal to 1, J runs from 1 to 6. When I equal to 2, J runs from 1 to 5. Similarly for Lij, the measured thing for Ij. Similarly for epsilon Ij, the errors, which are not measured, but you will need them when you want to write down the model. With this thing, now we want to write down the model. Remember, the box diagram dictates the data layout. The box diagram does not completely dictate the linear model. With the same box diagram, we may have different linear models. We have already seen that. Linear regression and quadratic regression both use the same box diagram. In this case, what should we do? Let's see. We have the idea that the springy nature of the spring, the elastic property, that will remain same in either lab. Indeed, that is what we are going to study. Possibly that is made up of steel, of a certain pitch and a certain radius. All those things are fixed, and we want to study the elastic property of springs with those things. The initial length is not of much importance. So in this case, a natural model will be this. Lij will be expressed as again a linear regression But the intercept term, which you understand, has to do with the initial length that is allowed to depend on I, that is the lab index. Then beta, which gives you the elastic property, that is independent of I. So this is what we are primarily interested in. So I have got alpha 1, alpha 2, I has two values. Those are parameters but not of primary importance in this example. Beta is the parameter of primary importance, then wij plus epsilon ij. So this is one possible model. If on the other hand you have a different setup, for example, you know that the initial lengths are the same, however, in one lab you are using springs made of steel, in the other lab you are using spring made up of some kind of, say for example, aluminium, in that case it is beta which will change. So this is that particular model that we are going to study. Observe that alpha, the intercept, now depends on I, beta, the slope, does not. Okay, so in this case, we first have to understand how the two data sets from the two labs are to be merged. Here I have got two files from the two labs. From lab 1, I have got this data set. From lab 2, I have got this data set, and I need to merge them. Here the data sets are both small in size, so what I can do is that I can just take these and just paste under them. That is possible, yes. But that's not the right way to do it, because in general your data may be huge and copying and pasting is not a very smart operation, especially if you have many such pairs to merge. So what we shall do is to employ R to do the merging. For that we will read both the data sets. So I will read them, F7, yes, I have read them. Let's quickly have a look at the two data sets, lab 1 and lab 2. Perfect. Okay, now what I want to do is that I want to put one under the other. For that the command is rbind, bind as rows. So I will create my data set, call it all lab, and that will be R bind, and then two things. Well, I remember suddenly that before doing that I have to carry out one more thing, namely I have to append a column of the lab, so I will do that beforehand. So I will just convert my lab 1 to this. So lab 1 modified, call it lab 1m, and I will call it data.frame. I am creating a new data set. I will take my lab 1, with it I will append one other column, I will call it lab equal to 1. So let's see what I am getting here, lab 1m. So it is the same data set as my original one, but I have appended one column of all ones to it. Now I could have overwritten it directly. I could have written lab 1 equal to data.frame lab 1, etc. But then the problem is, in case you wrongly type something, you might find that your original data has been overwritten by something garbled. That's why it is a good idea to use a new name, lab 1m. Well, you carry out the same thing for lab 2. So it is 2, and I call it 2. So this is your lab 2. Oops, sorry, I wanted to show you lab 2m. This is lab 2m. Now I take lab 1m and lab 2m and put them one under the other. So I will use the row bind idea, R bind. All lab equal to R bind lab 1m lab 2m. Let's see if we have got what I wanted. All lab, yes, I have got 11 cases, that is 5 plus 6, and the headings are as they should be, weight, length, lab, and all the things in proper order. So the next thing is that I should make some plots. Now since I have finished doing this, it's a good idea to copy paste these lines back to my script file in case I need them later. So I was not very sure if I was doing things correctly. That's why I wrote them directly in the command prompt, not to clutter my script file. So I'll just convert things back. Yes. So I read the file, then I created the combined file. Now I will make a plot. So plot height, length, and this length tilde wet and all lab. So let's see what I get. I have this plot. I get two lines kind of parallel as I expected. Now it would be nice if I can see them more or less clearly, so that the two labs are given to different colors. So I will give it color equal to, I will use which one? Lab. So let's try it again, see what I get. Now I get two different colors. I get black and I get red. Of course you can use other colors. You can look up the help of plot to see how the colors are chosen. But by default it will automatically give you these two colors. And if there are three, it will choose three colors and so on. So I've got two parallel lines. Fine. So what should I do now? I can try to fit my linear model, but there is a little problem. You remember, these things are actually factors, but since I've encoded them as 1 and 2, it will think that these are actually numbers. So 1 is the number, 2 is double 1, and things like that. But that is really not, lab 2 is 2 times lab 1. These are just used as a nominal level. That's a factor. So we should better tell R that we are working with factors. So I will do that. So I will say, what did I call it? Lab. Now I can use this syntax, which is save some typing. I will write with all lab. That is, I am working with the all lab data set, and I want to say lab is actually a factor. Lab is a factor version of lab. So with all lab, lab becomes a factor lab. Apparently nothing will really change. Oops, sorry. I gave eval substitute expression. That's always the problem. Yes. So in this case, because I am writing it inside a function, I have to use this arrow notation. So this will work. So either you can use this, or if you want, you can use the more verbose version, which is this: all lab $lab equal to factor all lab $lab. That's also possible. It will have the same effect. So both will have the same effect, that now it understands that lab is actually a factor. If you want to know that it is indeed that thing, you can, well, just print all lab. Nothing will change really. It still looks like 1, 2, etc. I think you can see it if you type class all lab $lab. It says it's a factor. If on the other hand you try length, then it says it is numeric. So now it understands it's a factor. Okay, so we are now in a position to apply our linear model. Let's quickly recall that linear model that we had. We had this: Lij equal to alpha I plus beta Wij plus the error. Now I want to specify this using our syntax. Let's see how we do that. I will write it here. Fit equal to lm. I will have length, no problem with that. I will fill up the rest and put all lab here. Now what do I want to put here? I do not have any interceptor, so I will put a -1 later. the very first term that I have in here is alpha I. I stands for lab. So I will write lab. Then the next term that I have is based on the weight. So I will just write weight. So I simply write length is lab plus weight, which in a sense reflects very nicely this box diagram. Length is the added effect of weight and lab. So this form is very well suited for the box diagram. If you have the black box diagram, you can immediately write down this form, lab plus weight. But if you want to compare it with this mathematical form, it is slightly more involved. Alpha I becomes lab, and this beta thing that becomes the weight. Okay, so let's just try it out. And let's see what is inside fit. Oh, I have made a mistake. Because if I do this, then it will have an intercept term. Let's just take a look at it. Yes, it has added an intercept term and lab 2. I do not want that. So you might be wondering what happened to lab 1, but let's not worry about that. For the time being, I will just subtract that 1, saying that do not add the intercept term. Now let's take a look at fit, and you will see whatever you wanted to see. You have got lab 1 coefficient that according to our parlance was alpha 1. So alpha 1 hat is 3.276. Alpha 2 hat, that is 5.173, and alpha and beta hat is 2.013. So this is how you get all these things. Now you might be wondering what happened there when I put that intercept term wrongly. Somehow magically it reported only lab 2 and not lab 1. That is indeed somewhat like a magic, and we shall take a look at that magic later. But for the time being, let's quickly see what is the design matrix that it is using. Model.matrix fit. Ignore all those attributes, ATTR. You have 1, 1, 1, 1, 1 for the first 6. So here you have got alpha 1, alpha 1, alpha 1, no alpha 2, and then the W1Js, W11, W12 up to W16. The remaining 6 entries, I'll make it larger, the remaining 5 entries, they come from lab 2. They do not have any contribution from alpha 1, they have only contribution from alpha 2, and of course we have W21, W22 up to W25. So the model matrix is exactly as we expected it to be. So it constructed the model matrix for us. That is a very important reason why we should use the LM function. We just specify the model, it creates the design matrix, or the model matrix as it calls, for us. Okay, so that's all for this session. Here are 2 problems for you to solve. In this example, we were using intercepts alpha 1 and alpha 2. Alpha 1 was specific to lab 1 and alpha 2 was specific for lab 2. Now suppose I tell you what alpha 1 and alpha 2 are. They are known, which is very natural because I am sure that you have noticed that alpha i's are nothing but the initial unstretched length of the 2 springs. So you might just directly measure them. So it's quite possible that you have already measured them, so you know alpha 1 and alpha 2 for sure. If that is the case, then you have only one parameter beta. Now can you express that as a linear model? Suppose I tell you that alpha 1 is 5 and alpha 2 is 10 or just whatever. So can you write that as a linear model and then solve it? The second problem is similar but slightly more difficult. We have already seen that alpha 1 is the initial unstretched length of the spring used in lab 1 and alpha 2 is the initial length of the spring in lab 2. Now suppose these two labs are situated far apart and the main investigator sits in lab 1 and a subordinate investigator was sent to lab 2. The instruction was that you should first measure the initial length before anything starts so that you know exactly alpha 1 and alpha 2. Maybe alpha 1 and alpha 2 are actually part of the specification of the springs themselves. So it is not measured, they are known exactly. But unfortunately, the subordinate investigator who was sent to lab 2 ignored that duty, forgot to write down the initial length of that spring. But in lab 1, the principal investigator has quite correctly measured that length. So you know the exact value of alpha 1, but you do not know the value of alpha 2. This is a very common situation where you have to carry out the experiment spread out over multiple labs, and in some of the labs, some of the measurements are not available. In that case, how will you cast this as a linear model and how do you solve it using R? So that is the second problem.